Hello, friends. I'm Ashish Tabari, founder and CEO of Aximize. To our new listeners, welcome, and to our old ones, welcome back. Today in the house, we have a fascinating technical authority in the field of portable stimulus. Yes, friends, I'm talking about none other than Adnan Hamid, founder and CEO of Breaker. Welcome, Adnan.
Thank you, Ashish. Thank you for having me.
Oh, it's a pleasure to have you. So you're the CEO of Breaker, and before we talk about the fascinating things you're doing now, I would like you to share a bit on your personal journey, where you were born, how did you get into science and engineering, um, anything you may want to share with our listeners.
Of course. So, yes, my story is maybe a little bit different from many. I was born in China, in Beijing, China, as the child of a diplomat.
Wow.
So, my parents were diplomats posted from Bangladesh to China.
Very interesting.
Then, around when I was 10, we happened to be posted back in Bangladesh at the time. And my mom was working with one of the first computers in Bangladesh, the third world country. Not we got them a little bit late. And at the ripe old age of 10, I learned BASIC from the famous Tandy TRS-80 manual.
Yeah. Yeah.
I didn't have the computer. I just took the manual, but it all made sense to me, right? You know how it goes with kids.
Sure.
And I quickly concluded that, hey, I can program computers fine, but what I really wanted to do was build the damn things. And that's how I got into science and engineering. So to evolve that story a little bit for our listeners here, I actually finished my schooling in the UK, up by your neck of the woods in Sevenoaks, down in Kent.
Oh, wow.
Finished that and went to college at Princeton, okay, on the East Coast of the US. So now that story relates a little bit to what eventually became Brecker, because I was at Princeton on scholarship, but needed money for books and clothes. So I ended up taking a job at the psychology department, working for $6 an hour as a programmer
Yeah.
for a professor,
Right.
who happened to be doing research in AI.
Wow.
Okay. And that guy, his name was Brian Reiser. He was actually working at the time on planning algorithms. So today, when we hear AI, we all think about deep learning.
Oh, yeah, planning.
But there are other branches.
Yeah.
This is one branch of planning algorithms.
Yeah.
Okay, so this is what I did.
Very nice.
So then, after that, I started my actual career at AMD after college. And what do they ask a new grad to do? They ask you to go write test cases.
Yeah.
I was too lazy to write those damn test cases.
Yeah.
But I said, hey, I know how to put planning algorithms to use to generate all the test cases I need.
Yeah.
And that evolved into a really nice solution. Okay. And over here is maybe the crux of the whole idea, right?
Mm-hmm.
With the planning algorithm, you start with what you want to check, and then you work backwards through a set of rules to figure out how to create a scenario that should give you that.
Yeah.
And this, in turn, gives you a single source from which you can generate your stimulus,
Mm-hmm.
you can generate your checking,
Mm-hmm.
and you can do deterministic coverage closure.
Yeah.
So those are your three big things. And then it turns out that the nature of these planning algorithms is it knows so much about what it's trying to do that you can generate high-level debug information, more abstract than looking at waveforms. And it lends itself very much to requirements traceability.
So wait a second. So sorry to interrupt you. So we are going ahead.
Please.
We are going ahead of ourselves here. There's a lot of fascinating stuff you talked about, which is your journey from UK, where we are based. I've spent many years in London, and you basically ended up in Princeton working at $6 an hour, and then ended up in AMD having to do the grunt work of writing test cases. But actually, the cusp of what you end up doing now is basically your introduction to planning algorithms, as you said, part of artificial intelligence for a very long time. And in fact, you're saying that is what was your main shall I say, the eureka moment, and you said, okay, let's take this further and use this to achieve multiple different solutions to problems that you were already seeing in the field. This is really nice. I didn't know that actually. I'm not an expert at portable stimulus, and we'll get into portable stimulus in a second. But I always wondered, looking at it from reading it and talking to you and others, is that there seems to be a lot of synergy with AI and planning. Because I've done something similar back many years ago, so I could see the correspondence. But let's dive into portable stimulus. So a lot of our listeners actually might not be very much familiar with portable stimulus, but they are familiar with dynamic simulation, UVM, maybe formal. So can we go down a bit deep, but at an introductory level, what is portable stimulus and why do you need this?
Yes, of course. Let me start by touching a little bit on what you said about planning algorithms, right?
Sure.
Because the fact is, there are no new ideas in the world, right? We just apply old ideas to new problems. CPUs were designed well before we could build them, right? A lot of the math we do in formal techniques were designed well before our computers were strong enough to do them.
Yeah.
So planning algorithms were developed in the mid-70s, I think.
Mm-hmm.
And yes, the only aha was apply a known body of work
Mm-hmm.
to verification.
Mm-hmm.
Okay. So now getting on to the question you asked, right?
What is
portable stimulus?
Yeah.
By the end of care, right? At the very highest level, portable stimulus is simply the next level of abstraction for verification. And the easy way to think about it, at least for me, is now we're all used to the idea of logic synthesis. We write RTL, we feed it to some tool, and out comes our gates.
Mm-hmm.
But it was not that long ago. It was only about 20 years ago that this was done by schematic capture, and that was just the way you did things, and that was actually the tip of the spear as far as technology goes, right? It was better than having to write netlist by hand, right?
Yeah.
But along came a high level of abstraction, and we got huge value from it.
Mm-hmm.
And now, wanting to go from 25 nanometer to 15 nanometer technology, we just press the button again, same RTL in, completely different gates out.
Mm-hmm.
Okay. The reason I bring this up is what I've been working on here for the last 15 years is what I call test suite synthesis, right? We take a portable stimulus model as input and synthesize closure on all the test cases that we need. Again, we'll talk a little bit more about what closure means, because that's a loaded point unto itself.
Mm-hmm.
So by abstracting the capture of the verification intent,
Yeah.
a lot less work, and you can cover all the different platforms.
Mm-hmm. So why is it called portable stimulus? So it's driven from requirements, and you're operating at the level of, hey, if you tell me your requirements, I can generate test cases in order to provide a complete coverage-based test infrastructure. But what is the stimulus world doing there? Because we're talking about the portability of requirements, isn't it?
Fair enough. Personally, I like the word portable, and I think the word stimulus undersells the whole principle, but it's the name that stuck. Okay. Let's talk a little bit about what is actually going on.
Mm-hmm.
Okay. So I'm a little bit trying to answer your question and get a little bit into why we need this.
Sure.
So the picture I want you to form in your head is, okay, ultimately we're building state machines, right? They're
Mm-hmm.
complicated state machines, but
Mm-hmm.
we're building state machines. Okay.
Yeah.
We can describe our intention for this thing, this product, this chip,
Mm-hmm.
this SOC, this device, whatever
Yeah.
level of hierarchy you add,
Correct.
it doesn't matter.
Correct. Yeah.
You can describe its requirements as a flowchart.
Mm-hmm. Mm-hmm.
With some configuration, given some configuration and some input, you should see some
Mm-hmm.
output.
Mm-hmm.
And we could draw this on a whiteboard
Yeah.
as an chart.
Yeah.
Okay. Now, as we get into this, we would say, okay, yes, but there are many options for each configuration. There are many options for each input. There are many options for each output, and there's some relationship between which ones, which configurations, which inputs, and which outputs go together.
Right.
But the fact is this, that we don't train DV engineers to think like this formally, but we do this. This is what we all do in our head, which is what's the output I'm trying to check.
Right.
Therefore, what input do I need and what configuration must I set up?
Right.
Okay. If you can capture that flowchart, then what you're trying to do is make sure you've tested all the paths through that flowchart.
But hang on a second. See, we are actually not thinking about stimulus necessarily at the flowchart level at this point. We're thinking in terms of what outputs we need, and of course we have some idea of what is the nature of the inputs driving this design or a SOC or whatever level of abstraction we are talking about. But we're not necessarily thinking in terms of sequences yet. We're purely thinking in terms of relationship between I/O.
Oh, I love that point, right? So usually when the sequences in our industry, we are specifically meaning UVM sequences, right?
Yeah, I know, yeah.
And but that's not enough, right? We have the UVM sequence at the block level. We want to do subsystem sequences. We want to do full chip often with software-driven tests. We need to go to emulation. We need to bring in the firmware and so on. So that's the whole point of saying abstraction. We got to move above the mechanics of how the test bench works.
Cool. Yeah, that's what I was expecting. Yeah. Carry on. Yeah.
So yes, we are well above the test bench mechanics. Okay? And really, if there's one takeaway for our listeners, for me, it's look, get up above the test bench and think about what we got to get done, right?
Excellent.
And think in terms of that flow chart of things we got to cover, right?
Yeah. That's how I think. That's how I think about verification. Yeah.
Once you wrap your mind around configurations to inputs to outputs, and you're trying to cover all the paths, okay, you got to do a little bit more. You got to have hierarchical flow charts because we do complicated things. You got to recognize that different paths represent different product requirements for requirements traceability, right? Why do we have this configuration with the possibility of this input is to satisfy a particular requirement, right? And we have to consider concurrency across the scenarios.
Yes.
But this is basically the idea.
Yeah. So this is really awesome. Let me pause you for a second. So this is all going down in the right direction of requirements-driven design, requirements-driven verification, and this ties very nicely with all of these industry standards like ISO 26262 or the DO 254. So this is very, very nice. This is absolutely the right way to approach the verification problem. So I can see these two as being primary reasons. What else do you think were the reasons for you to be actually going fast with this? Were you noticing bugs that were being missed in silicon using conventional verification? Was that the driver for you to speed up this development?
My real driver, back when I started, was I was too lazy to do the work the other way.
Right.
What is that? If necessity is the mother of invention, laziness is the father.
Yeah, that's it. Yeah, that's a good
translating that into practical knowledge, right? If you are a verification manager, why would you even consider looking into this?
Right.
And the math is very simple.
Yeah.
We've known for decades so verification is 70% of our budget in developing product.
Indeed. Yeah.
You dig into the Wilson research data and you find that over 50% of that 70% is in developing and debugging test content.
Yeah.
People spend a lot of time doing that. And you have many environments, right? You do this over and over again. You do it block, a subsystem, net system, you do it in simulation, emulation, FPGA, silicon with firmware. So you're repeating that 50% work over and over again in each platform. The notion of using a single source to synthesize the right output for all those platforms is clearly what is needed, right? That's a jump we're making with portable stimulus.
That's a very big jump. That's a very big leap. That's basically saying, I think this is like saying this is the universal language that will actually cope with different levels of abstraction, going from IP all the way up to the full system. And you're saying you're
We
building
must.
yeah. You're basically saying it's a universal framework, and it's funny how UVM is called universal verification methodology, but I sometimes don't find it universal enough. I find it very.
Not touching that.
No, I mean it's probably universal in a certain context, of course, in the world of many universes, right? But I think what you're saying here is in, I don't know, maybe I'm looking into it in a way that you may not be indicating, but I think what you're saying is come up with a way of describing these requirements driven scenarios so that you can break them down to the level of IP, block, subsystems, all the way up to systems and firmware, which is
Yes.
actually very well. So, how old is portable stimulus, Adnan? How long have you been doing this?
The true history of this is I started with this planning algorithms for test generation. Was when I started the Brecker, the company. Initially, we were applying this at the IP level, and we were working with ST. And ST came to us and said, "Hey, this is really useful at the IP level. Can you also generate for me my software-driven test so I can run the same IP from the CPU?" And since my background was from at AMD, when we were using planning algorithms, we were generating assembly code, so we were just used to doing this.
Yeah, okay.
So the fact is, we did the software-driven stuff overnight,
Right.
and then later figured out that we did something useful. Okay,
No, I see. Yeah, I totally see. No, I totally see what you're saying. So all in all, what we're saying, what, 10 years, 20 years?
I would say about 10 years.
10 years.
10, 15 years, 10, 15 years. It all depends on where you count from, right?
Yeah.
I've been selling product in test rate synthesis since about 2008. So that's 12 years.
So I can't quite put a hand on when I started to hear about portable stimulus, but now almost every big conference you go to, there has to be a track and a panel about portable stimulus, and some of my other partner companies, EDA companies, are also heavily investing in this. So I can certainly see that this is the future of how things are going to evolve. So let me move on to another topic, Adnan. And I know we've talked about this before. A lot of the terminology and concepts with portable stimulus is about it being declarative, it's compositional, driven from requirements. Actually, all of this is stuff, as you now told me, you've been reading the same books, it looks like I've been reading. So we've been talking about this in the formal methods area for 4 decades or more. And I always thought we should try and use the collateral that you guys are building in portable stimulus to somehow tie this with formal verification. So what are your thoughts on this? Could we actually use a lot of these requirements or specification schemes and synthesize our assertions and covers? What's your take on that?
Definitely. I think I greatly agree with you. I mean, the fact is that this whole planning approach of start with a check and work backwards to figure out your stimulus is the same concept as the assertions and constraints.
Right? Yeah. We don't actually talk about stimulus in formal because stimulus comes to us for free. We just talk about blocking the stimulus. That is illegal. And we think
you talk about constraints.
Yeah, so we basically say, constraints. What constraints would be needed? What is it we're going to verify? What is the requirement?
Yes. But you're constraining what can come in, and you are asserting that if these legal things come in, that you have some properties allowed.
Yeah, exactly. I think the biggest win, I mean, the way I look at this is where we are winning against simulation is that we don't have to actually spend time designing test sequences because they come to us for free. Informally.
Yes.
And that's a very big win.
It covers all of the space in one go.
That's right.
So it is huge, and I'm not an expert, but I'm a big fan, right?
The two worlds seem quite isomorphic at times. So this compositionality aspect of portable stimulus, do you use that a lot in either the tool chain or in actual specification frameworks?
Composability?
Yeah, composability. Yeah.
It turns out to be a primary anchor of the whole thing working. Okay, I mean the easy way to think about it is you go build some model for a UART, you go build some model for a DMA, you test each of the IPs separately. When you're in the SOC, you want to see that input from the UART can be moved by the DMA and vice versa. So you've got to plug these things together. So it's not a, hey, here's a feature we use quite a lot. It is a little bit the anchoring idea over here. Right? Or go the other way, right? At the just like anything else, you use the V model, right? You architect top down, bottom up, and you might be starting with your requirements instead of breaking that out into, okay, this is how my model's going to look, and then start populating them bottom up. So I think it's very fundamental.
So two things come in my mind. So when you're talking about specification of requirements in the portable stimulus flowchart type, and now we're talking about compositionality. Are we capturing temporal specifications as well in portable stimulus? And what about composition over time? How do we handle the fact that actually...
This is a great question, and the answer is yes.
Okay.
Portable stimulus definitely must reason about time, or we must do closure on time. But having said that, we also need to be aware that we're talking about an abstracted concept of time.
Correct.
A starts at the same time as B. A starts after B. You probably don't want, you could capture it, but you probably don't want to say A happens 3 cycles after B.
No, we don't want the cycle level. Yeah, we don't want that level of granularity.
Because you can't take that up to silicon, right? You don't have control.
No,
right?
Yeah.
So yes, we have ordering information, we have concurrency information, and that in turn lets you go think about measuring temporal coverage, measuring what's the word for this idea of interleave coverage, right? I have sequence ABC, I have sequence 1, 2, 3. What are all the ways that those things could interleave? Right?
So this. I mean, you're familiar with CSP, communicating sequential processes, and a lot of work done by Robin Milner back. And then we have EventB, which is another framework. And a lot of these frameworks allow similar way of capturing temporal specifications. And it's like a refinement-based approach. You start with very abstract specifications, and you can refine them and make them more and more precise and add more granularities of time. Is it something similar you're doing in the portable stimulus framework?
So I think, again, you're on to a very important question. So first of all, I'm not deeply familiar with the 2 frameworks you talked about, but I am certain that the answer to your question is yes. Okay. But I do want to put a spin on it. The thing with portable stimulus, it's a little bit like the thing with Verilog. It's not about teaching people languages. It's about having a language that people can use.
It's a methodology.
VHDL was a, quote, better language, unquote, than Verilog, because it was more formal, more structured, more complete, and no one could write it, right? Verilog, from a tool perspective, from an analysis perspective, is, it sucks, we can't make sense of anything going on, but people know how to program, right? So in portable stimulus, we need to be able to fork and join threads just like we're used to in C++. System Verilog. System Verilog's fork is more constrained, right? More structured. But the point over here is don't ask human beings to learn the tool. Have the tool work the way the human beings are used to programming. And with portable stimulus, we have to come back to your conversation about formal, but in portable stimulus, this need is much higher than any other tool because you have such a wide audience, right? You want to talk to the UVM guy down at the IP level. You want to talk at the bare metal C guy doing system integration. You want to talk to the driver guy who's a full software guy. He's not going to learn some deep declarative thing, but that's cool. We know how to take Verilog and synthesize logic, right? We can take regular languages and sort out what they mean and generate all the things we need.
I'm pretty sure there is correspondence because this concept of fork and join and other such. I mean, basically, you're using a concurrent language framework, which is what the languages like
Absolutely.
NP and CSP they provided. But let's move on to other things before we run out of time.
Yes.
I know you're quite busy, and so we have to get you back, Adnan, because I think we've only just literally touched some of the topics in a very fleeting way. But it's okay. I think that for a lot of our listeners, this might be the first time they're listening to Portable Stimulus. But tell me if actually a listener today wanted to take away 5 tips from you to become productive with their DV. What would be your advice? What would be those 5 tips, Adnan?
I'll give you 3.
Sure.
Okay. First, take a step back and look at what you're doing. Okay. Recognize the distinction between what is your test bench and what is the content you're running on that test bench. Recognize how much work you're putting into that content in terms of writing sequences, writing your checkers, writing your coverage models. Today, we're just told that's what you have to do, so we go burn lots and lots of people doing it, right? And then look at how many times that same work is repeated, right? You'll write a USB test at unit level, you write it at full chip level, you write it again in diagnostics. So just look at that and consider that that's a huge waste and that there are now better ways to approach it. So my point over here, my first point is take a step back, look at where you're burning time and people, and that there is a better way to do it. Okay. My second point is step back and think a little bit about your verification planning, right? I'm not talking about tools that let you capture trees of requirements. This whole idea of, okay, let's start with our requirements and our features. For each of that, let's break that down into what we have to check to know the feature is working. And to check that, therefore, what stimulus must we drive? We know we have to do this, but this is not how we think. We go write our list of requirements and features. Separately, we go develop randomized stimulus. Separately with the checker, and then we go say, okay, how are we going to cover this thing? And we have a big mess, right?
Right. Okay, indeed.
And this is a very good logical way of thinking through your planning. And then once you get through there, then realize that you can capture that plan directly as flowcharts and synthesize all the tests you need.
So shouldn't verification planning then take the shape and form of these flowcharts, as opposed to then shouldn't they be the most canonical form of entry into the whole verification activity? That's what
that is my thesis, right? Exactly, Ashish, right? Once I mean, that's maybe a little bit the point of my the idea behind my 3 points, right? First, realize that what we're doing is in the Stone Ages. Second, go think about how you should be thinking about your plans. Right? It's obvious to you what I said is right, but it's not what we do. But once you think it out that way, yes, that is a flowchart. I described a flowchart in words. And from that flowchart, that becomes your executable specification. Turns out that you can draw flowcharts and simply generate the portable stimulus model. And from that, we can go generate all the test cases. And these are all the stuff we've pioneered. But that's detail, right?
Correct.
That's technology.
Correct.
And technology is always detail.
Correct.
And the big value over here is you get deterministic coverage closure. Right? Today, it's just throw the dice, see whether you got what you wanted. Use a lot less people, a lot less time. And then one that I think is under-recognized, you preserve knowledge. You take a USB expert today and he does all your tests, he takes off, goes to his next company, and you're going, well, we don't have anyone who knows how this thing works.
Correct.
If you have the flow chart, it's got to capture it. So, So to summarize, right, take a step back, see how wasteful the efforts we do today are. Take a step back, look at how verification planning should really be done, and then realize that if you plan it the way you and I are talking about, you can generate tests directly from that plan.
Awesome. So actually, what you said is nailed down in 3 different artifacts, which I totally agree. Take a step back, think about verification planning, think about reuse in a sensible way, not in a wasteful way, and think about this in a documentation-oriented way. All of
Yes.
this actually looks to me very, very necessary, useful stuff. But now I'm not sure how long it would take the collective of all of our practitioners in the industry to make these changes happen, because change is very difficult. COVID-19 has enforced a change on the whole humanity, but what you're actually saying is we need a big change, and as you said, from Stone Age to the New Age, as it were. Do you really believe we can actually make that happen? And how long do you think we could before we just wrap up our chat today? That would be an interesting parting thought, actually.
This is change management.
Yes.
Very important concept.
Hmm.
Okay. And the good news over here is, the game doesn't have to be that you go change everything you're doing across the company overnight, because that simply will never happen.
Hmm.
Right?
Hmm.
The tools we build, they synthesize test cases for existing test benches.
Mm-hmm.
So you could be carrying on building, you might have a UVM environment, you carry on running your own UVM sequences, and now you have this source of, you had 100 UVM sequences, and for about the time it took you to write the 101st UVM sequence, we can generate 1,000 of them,
Mm-hmm.
right?
Mm-hmm.
And so, and then we can, you have your full chip environment that's running C programs, and you press the button from the same model, and you have C programs that run on that environment. So what we have found is the value is obvious in a sense, right?
Mm-hmm.
Reuse has to be good, abstraction has to be good, synthesis has to be good. These points are not, nobody's going to argue with them,
Mm-hmm.
other than applicability.
Mm-hmm.
What it takes is a hard problem. So problems where human beings are having to write thousands of test cases,
Mm-hmm.
thousands of sequences.
Mm-hmm.
If you need 100, this is not where you start, right?
Mm-hmm.
You need an early adopter, right? You need somebody who wants to make the world move forward.
Mm-hmm.
And then you apply it in one place,
Yeah.
right? Or you apply it in two adjacent places,
Mm-hmm.
right?
Mm-hmm.
In fact, what I usually look for is a problem that requires large suite of tests and has at least two platforms, right? UVM to full chip, or simulation to emulation, or
Right.
emulation to post silicon.
Okay.
And that's a way to take a baby step forward, prove for the thought leaders to prove to their management, hey, this makes a difference, we ought to do it. And that's how adoption happens. But I didn't tell you anything new.
But actually, this is the thing, Adnan, right? What you're saying is target the areas where you have lots of test cases, where you have a blend going from simulation to emulation. And those are areas, these are tips that managers and senior verification leads can take from our discussion, is if they want to go and actually evangelize, deploy portable stimulus, and I'm wondering, where should I start from? This is the point to start it from. And this, I think, is important. I mean, we're not going to change, we're not talking about a revolution, we're talking about a structured evolution, right? And we're looking at deploying it in a sensible way so people can take value out of it and see it for themselves. And that's pretty much what I would expect. I mean, from a formal verification point of view, whenever I'm trying to get this deployed, this is how my approach is. Anything new for that matter, right? We've got to understand that people are used to old ways. But man, great, fascinating chat, Adnan. I know our time is running out today, but thank you very much for your time, Adnan. And if you are going to be slightly less busy, if you can squeeze out another half an hour for us later this year, we will continue where we leave today. But for today, thank you very much, Adnan. Thank you.
Thank you, Ashish. Okay.
So I hope, friends, you liked today's podcast. We had a fascinating discussion on portable stimulus, where it came from, and how it could be deployed in practice in your projects. So let us know by emailing us at info@aximize.com. Follow us on our Aximize YouTube channel, and let's stay in touch and keep healthy. Thank you very much.